Hi, this is Group 14 Celeste with the group members
Carl,
George,
Jennifer,
and Dina. This is our code implementation for the project course SYSC 4805 for the autonomous Snowplow robot. This is the header file which contains all the includes from the external libraries as well as the defines for constants and the pins that are used. These are the constant values used for motor speed, direction, and angle, as well as sensor, threshold, and pin numbers. These are all the global variables that we're using. We have an average, which is average of all the readings for the line follower sensor. White, which is the initial reading of the white floor from the line followers that we use as threshold. We have the semaphore, which is the lock to make sure both tasks don't access the shared data at the same time. Volatile flag for line detection, volatile integer for what the current obstacle is, and robot state as an enum. The program enters at the setup function.
So I'm going to start off with the set speed. So the set speed function basically controls the rotation speed. It uses the function analog right to set the rotation speed of each of the pins in the DC motors. As you can see in the screen, you have analog right, SPE underscore pin 0 left. So this is basically the left motor. Then you have the right. Then the set direction function. The set direction function basically controls the direction for the motors. It uses digital right, basically indicate if the motor is going forward, backward, reverse, or a turn. Then you have the getLine function. The getLine function basically takes inputs using the analog read function from the 3 pins on the line sensors. So you have out 1, out 2, and out 3. Then we take the average of the 3, and then that average is what we're going to use to basically indicate a darkness or lightness.
The poleLine function calls the getLine value and checks to see if there is a line there. If the line is above the threshold, it'll return true, otherwise false.
the pole obstacle function checks the ultrasonic sensors to see if there's an obstacle. Here it's checking for the first ultrasonic sensor. It compares the value received from the echo pin on the ultrasonic sensor with a calculation done using the speed of sound to determine the distance away the obstacle is from the robot. It does the same for the second ultrasonic sensor, and then it compares these with a distance threshold, which is predetermined to determine if we're close enough to an obstacle on either the right or the left of the robot.
The getThreshold function initializes white floor threshold. The stationary turn function sets the direction for a stationary turn. Right turns will cause the left wheels to go forward and right wheels to go backward, and left turns will cause the left wheels to go backward and the right wheels to go forward. V-task delay is a non-blocking form of delay that allows a task to yield control back to the CPU while it completes its movement. Doing so allows another task to be scheduled while it's doing its movement. The move reverse function sets the direction to be in reverse and it allows the robot to move backward.
The init pin function initializes all the pins mentioned in the headers.h file as input or outputs respectively.
This is the startup function. In this function, we set a baud rate for printing to the serial monitor for testing purposes. We set a random seed, which we use for everything random in our system. We initialize the pins. We get an initial value for the floor with the get threshold function, and we enable the watchdog timer.
Then we have the tasks that handle the core functionality of the robot. We have the pull sensor task, which will pull both the sensors and store their values, and then lock the semaphore and save it to the global variable before yielding control back to the CPU. And then we also have the task for the main robot logic, which is implemented as a state machine. The robot, in its forward state, will move forward and it'll lock the semaphore and check to see if a line or an obstacle is detected. If so, then it'll switch its state to reversing. In its reversing state, it will move backwards for a set amount of time before entering its turning state. In its turning state, depending on what obstacle was detected, whether it be a line or an obstacle, for a line, it will stationary turn to the right by 90 degrees plus 15 degrees times some random amount to give a turn of either 90 degrees, 105 degrees, 120 degrees, or 135 degrees. If it's an obstacle, it'll turn 45 degrees always. Depending on whether the obstacle was detected on the left, it will turn right. If the obstacle was detected on the right, it will turn left before changing its state back to forward and yielding control back to the CPU for another task to be scheduled.
And finally, we have the setup function. The setup function basically implements free RTOS logic. It performs all the configurations and setups. So from the code, we have a function called xSemaphore create mutex. This basically creates a semaphore function. And what a mutex does is that it protects any shared data from corruption or race condition. Then going into the if statement, we have xtasks create, which basically creates a task. Then we have vtask start scheduler. So what this function does is that it calls the scheduler, which then starts the task. And the scheduler basically determines which task starts first. So it could be any of the tasks that has been created. Then lastly, we have the loop, which basically continuously executes the function.